Hello everyone. With this video, we are going to start our final chapter in this course. And in this particular chapter, we are going to see some concurrency control techniques. Okay. So more precisely, we are going to see two concurrency control techniques, one of them being two-phase locking protocol and the other one being timestamp ordering. Okay, let's get started. The first concurrency control technique which we are going to focus on is called as two-phase locking protocol. Right? So as the name itself suggests, the two-phase locking protocol is an locking mechanism, right? And we'll try to put locks in a way that we achieve conflict serializability, right? And we'll also discuss what parameters should we consider to ensure even recoverable schedules and preferably cascadeless schedules also. Okay, so first few simple things. So in its most simplest form, two-phase locking protocol has locks, as you can guess, and the two basic locks which are used is one is exclusive mode, the other one being shared mode, right? So in a shared mode, data item can only be read, okay, and before you read any data item, you must issue the or you must request for a shared lock, okay. And then in exclusive lock data item on which you place an exclusive lock, you can both read as well as write on that particular data item, okay. So in a typical implementation, what happens is that as your program tries to read or write any data item from your database, the the program requests for these locks, either shared lock or exclusive lock, to the concurrency control manager, and then only after your lock has been granted, the program will go forward and perform either read or write, right? But you will not see all of these things up front. These things are actually sort of coded inside your database system. Okay, so let's see more on these locks, right? So the shared lock and the exclusive lock, they both of them together, they can be put into something called as an lock compatibility matrix, right? So the way to read this lock compatibility matrix is as follows. So over here, you assume that a transaction is holding either S lock or X lock, right? And then there is another transaction. Let's say this is T1, which can either hold a shared lock or an exclusive lock on a data item. And then there is another transaction T2, which is either requesting a shared lock or an exclusive lock on the same data item, right? So the way to read this lock compatibility matrix is that if a transaction is holding a shared lock on a data item, then any other transaction can also get a shared lock, but it cannot get an exclusive lock, right? And on the other hand, if a transaction is holding an exclusive lock, then other transactions can neither get a shared lock nor can they get an exclusive lock, right? So that is why both these cells are false and false. Okay, now typically what happens is that if locks cannot be granted, then the transactions wait for those locks. We'll get more of this uh, when we talk a little bit about the implementation details. Okay, but for now, just focus on this lock compatibility matrix, right? So now, given your lock compatibility matrix, we are tasked with the job of putting the locks, right? So let's say you might remember these two transactions from our previous video. So this transaction is the same old transaction where $50 is being sent from one account to another, whereas this transaction T2 is just trying to read the account balances and then uh, display this sum, right? And if you remember from our video, our goal was to allow concurrency between these two transactions such that the equivalent schedule is conflict serializable. So that was the aim. Okay, now under that aim, and armed with your new uh, log compatibility matrix, how would you put the logs, right? So in this particular slide, I have illustrated an sample mechanism to put our logs. So basically what is happening is, here is that let's say this transaction T2, it wants to read a data item, it will request for a shared lock. If the shared lock is granted, it will read this, and then immediately after this read operation is done, it will unlock. And then similarly, for reading the account balance of B, it will again request a shared lock. If it is granted, it will read that balance and then finally unlock, right? And then finally it will display the sum of balance in account A and B, right? So that is T2. And then in transaction T3, which is trying to send some $50 from account B to A, what we are going to do is that, since we want to have writing privileges on this account balance, we will request for an exclusive lock. If the exclusive lock is granted, we will read, do the update, and then write the updated value also. And then immediately after this write operation, we will release this uh, exclusive lock on B. Similarly, when you have to put in the amount in account A, you will again request for an exclusive lock on A. If you are granted this lock, you will read that, you update the value, and then unlock, right? So this is a simple mechanism of how you are requesting for locks, and then how you are releasing the locks, right? So now this may look okay to you, but it so happens that even with these kind of locks, your conflict serializability is still not guaranteed. Okay, so in this particular example, I also write it over here that even with these locks going on, the entire transaction T2 can be executed between these two steps, right? So because by this stage, all locks on B are released, so transaction T2 can get those locks, and transaction T3 never even started requesting locks on A. So the whole of transaction T2 can be executed between these two steps. It can happen, what can happen, your T3 can get descheduled after this process, after this operation, and then the whole of T2 can get executed in the middle. It is possible, right? And now what happens if something like that goes on? Your conflict serializability is not ensured. And why is it not ensured? Because here the amount was deducted here, but it was not added here. So if you run this transaction in the middle of this, it will not be equivalent to any serial schedule. Okay. So just having a lock compatibility matrix does not get you conflict serializability. That is the moral of the story I want to give you here, right? The same thing is written over here. Okay, so in order to address that problem, people came up with something called as two-phase locking protocol, right? So in a two-phase locking protocol, what happens is that your transaction will try to get locks in its first phase, called as the growing phase. So here transaction will keep on getting locks, but it will not release any lock. The moment it releases a lock, it is not allowed to take any more locks. So that goes into the shrinking phase, right? So that's why in two-phase locking, your transaction will obtain locks in its growing phase, but it will not release any locks. Even if the job is done for with that data item, it will still not release any locks, right? And the moment all the work is done, in the sense that whatever locks a transaction wanted to get, if it gets all those locks and the job is done, then it will slowly it will keep releasing all the locks, right? So this is called as the shrinking phase. So let's show you an example, right? So So these are the same two transactions, T2 and T3 from before. Now, if you were to put two-phase locking on these transactions, right? Then what will happen is that this unlock which you earlier did after you were finished with reading of data item A, this unlock is not allowed anymore, because here after you are doing unlocking, you are again trying to get a lock, right? So this is not allowed. So in two-phase locking, you keep on accumulating all the locks. As long as you need even one more lock, you are not allowed to release anything. The only after you have acquired, only after a transaction acquires all the locks that it needs, and does those read or write operations, whatever it is, then only it will start unlocking, right? So this unlock would not be allowed. So unlock will be shifted here. And similar is the case for transaction T3, right? So here, when you wanted to update this value of B, we got an exclusive lock, we updated this value, and then previously we used to release this lock. But in two-phase locking, this is not allowed anymore, because there are further, operations down in your transactions which require new locks. Okay, so this unlocking would not be allowed in two-phase locking, right? So unlocking will only be done after all the locks which you wanted have already been achieved, and whatever you wanted to do with those data items, you have done those operations. Then at the end you will start releasing these locks, right? So what happens is that if you put your locks in this manner, in according to two-phase locking protocol, then it has been shown that uh, your whatever resulting schedule that may come out of this kind of locking is always guaranteed to be conflict serializable, right? So as I have always said that concurrency control manager does not have the power of scheduling transactions, right? Because that is something which is left to the CPU scheduler. There can be something like a round robin which is going on, or process can be scheduled if it is waiting for an IO or something like that, right? So all the two-phase locking protocol ensures is that the way the locks are put, and the way they are released, what we ensure is that the interleaving which gets generated, or which can get generated after two-phase locking protocol, is guaranteed to be conflict serializable. So that is the theoretical claim, or theorem that people have proved, right? So in fact, there is the statement also that transactions can actually be serialized in the order of their lock points, and lock points is defined as the point where a transaction has acquired all its locks. Okay, we will not go into the proof of this, but what you should remember is that by putting locks in this manner, and releasing the locks in this manner, two-phase locking protocol ensures conflict serializability. Okay. Okay, so now let's study two-phase locking from the perspective of recovery, because we, as we said before, just ensuring just conflict serializability is not the end of the story, right? So concurrency control manager should uh, achieve both conflict serializability, and it should also help in recovery, right? So both things must be covered, right? So let's see, let's try to study two-phase locking from the perspective of recovery, right? Okay, so let's see this particular schedule, right? So T3 executed first. We followed the locking as per the 2PL. Okay, by the way, I will use the short form 2PL for two-phase locking. Okay, so over here in transaction T3, we are following 2PL in the sense that we are obtaining the locks in the growing phase, and then releasing the locks in the shrinking phase, and so is T2. Okay, uh, But does this guarantee recoverability? Watch closely. No, it does not guarantee recoverability, because see what's happening here. So T3 did some updates on data items A and B, and T2 has consumed those updates, and then it has released the logs as per the 2PL, and then it decided to commit. Whereas T3, for some unfortunate reason, has now aborted. Right. So what did happen here? So T2 consumed something which was an output of T3. Right. So T2 consumed the output of T3, and it was allowed to commit before T3. Right. So this is against the very definition of a recoverable schedule, because if you remember, our durability clause in asset properties say that once a transaction is committed, you should not roll back. Right. So once a ticket is generated, you should not get an email that your ticket has been cancelled. Okay. So this commit was not allowed, and if you see closely, this commit and abort, it has nothing to do with 2PL. Both these transactions, they are inherently following the policies of two-phase locking, right? It's just that the commit operation happens to be in a way that it completely throws off. Even though this schedule is conflict serializable, it is not even recoverable. So this cannot be allowed. So two-phase locking in its basic form cannot get recoverable schedules. If it cannot get recoverable, you may even forget about cascadeless. Okay. So now let's try to see, what can be changed to get, recoverable schedules, and, preferably cascade. So it so happens that, we can change the 2PL with a simple tweak, and then we can even guarantee strict schedules. If you remember, in our classification of schedules according to recoverability, strict schedules was the best one. Okay. uh, First one was recoverable schedules, and then inside recoverable, we had cascadeless recoverable schedules, and then finally inside cascadeless we had strict schedules. Okay. Now, all we need to do is that, make a small tweak. So in two-phase locking, if we add a clause that all exclusive locks must be held until your transaction commits, right? So if you make just this change, then what will happen is that these unlocks will not happen here until unless the transaction commits, or in other words, these I should use them over here. These unlocks will not happen until and unless the transaction commits, right? So if these unlocks do not happen until T3 commits, then these dirty read operations will never even happen. The resulting schedule uh, will be certainly recoverable. It will also be cascadeless because you are not doing dirty read, and then it will also be strict schedule, in the sense that since these unlocks, these exclusive unlocks are not done until commit operation, that even satisfies the strict schedule definition, which said that you should neither do dirty read nor dirty write. Okay. So this is called as strict 2PL. You should remember this clause very carefully. All exclusive locks must be held until the transaction commits. It's just the exclusive locks. Read locks can be unlocked, right? Okay. So there is even a much more another variation where all locks are to be held until transaction commits. So this is called as rigorous two-phase locking. But if you ask me, I think this is good enough, right? So from the perspective of conflict serializability, you got conflict serializability, and you are getting strict schedules, which is the best for recovery process. So in my opinion, strict two-phase locking clears all your constraints with the highest possible scores. Okay, so just some implementation details with regards to locking. Okay, so here in two-phase locking, whenever things are implemented at the database level, we implement two-phase locking with lock conversions. Okay, so how does this lock conversions happen? In the first phase, you can acquire a shared lock or you can acquire an X lock, and then you can also convert an S lock into an X lock, right? So this is called as a lock upgrade, right? And then in the second phase, you can release either a shared lock or an X clause, whatever you want, and then you can downgrade an X lock to an S lock, right? So so this is how two-phase locking works with lock conversions. Right? So just an implementation detail. Right. Okay. So in the next two slides, what I'm basically doing here is that I have put some kind of just a pseudo code. How the locks are acquired. Right. So if a transaction TI wants a read lock, right, then this is how it is proceeds. If TI already has the required lock, then you just go ahead and read it. Else you need to wait, right? That's what the else part says. If necessary, wait until no transaction has an X lock on D, right? So when this happens, you can get your shared lock on D and then perform the read operation, right? So this is just, again, as I said, just implementation details of how a read operation will actually work under locks, right? Similar is the case with write locks, right? So if TI has the required lock on the data item, then just go ahead and do the operation. Otherwise, you have to wait, right? And since we want to perform the write operation, we have to wait until no other transaction has any lock. Right, so here note that we were just waiting until no transaction has an exclusive lock on D. But when you want an exclusive lock, you have to wait until no transaction has any lock on D. Okay. And now when when we are doing this with lock upgrades, then we check if the TI already has a shared lock. If the TI has a shared lock on D, then we try we will upgrade the lock to X lock. Okay. Otherwise, we just get the X lock. And so this is just implementation details. Okay. So far, we have seen how to use two-phase locking to ensure conflict serializability, how to use two-phase locking to have, strict schedules, right? And then, we saw some small slides on the implementation details of locking, right? So that so far so good. But, it's not all smooth. So whenever you are using locks, and this is true for almost any protocol which uses locks, right? So whenever we are using this kind of a shared lock or exclusive lock and multiple transactions are trying to get it, release it, and so on, there is always a chance of deadlocks. Okay, so here is an example of a deadlock in two-phase locking protocol, right? So here what has happened is T3 got an exclusive lock on B, it did some operations, it wrote it. Meanwhile, it got descheduled. So T4 got a shared lock on A, read A, and then again obtained a shared lock on B. Sorry, not obtained, attempted a shared lock on B, right? And given that transaction T3 is holding an exclusive lock on B, this shared lock cannot be given to T4, right? So T4 goes into wait. Now, as T4 is waiting, your CPU, schedules T3 back again, and then it requests for an exclusive lock on A. But again, as you can guess, we cannot give this exclusive lock on A because T4 is holding an uh, shared lock on A, right? So this kind of an you know this kind of a scenario where T4 is waiting for T3 to get a lock and T3 is waiting for T4 to get a lock. This is a classical case of an deadlock. And I think you must have studied the deadlocks in your operating systems course also. And as you know, whenever deadlocks happen, your transactions cannot proceed, right? And how do you address a deadlock? You have to kill one of the transactions. That is the only way, right? So either T3 or T4 must be rolled back and all its locks should be released so that the other one can proceed. Okay. So now whenever deadlocks are a case, we have to be a little bit uh, sensible in the way we are rolling back transactions, or in the way we are addressing the deadlocks, right? Because if we are not smart about our policies with the deadlocks, there is a possibility of an starvation. Okay, and this slide actually shows some examples of how starvation can happen. So imagine that there is a transaction which is waiting for an exclusive lock on a data item, right? And it is in a deadlock with some other transaction, right, which is holding an shared lock on an item. Now, while this deadlock is happening, other transactions can in theory keep getting the shared lock, because shared lock they are compatible with each other, right? So now what happens is, this guy, it's in the deadlock, and even if you kill and restart this particular transaction, it will have to wait for that X lock for a very long time, right? So this is a case of how in some cases some transactions may actually end up getting starved for a data item. Okay. Okay, so in deadlock handling, there are a set of policies called as deadlock prevention protocols, which a database system implements, and in some sense, these are pretty much the same as what you might have studied in your operating systems class. Let's take a quick look for this prevention scheme. So the first one being wait and die scheme, right? So here, what we do is, the older transaction may wait for the younger transaction, and this older and younger is defined according to the timestamp when the transaction comes in, right? So an older transaction may wait for the younger transaction to release the data, and older means smaller timestamp or the earlier timestamp, but younger transaction will never wait for the older ones. They are simply rolled back, right? So this is called as an uh, wait and die scheme, right? And then there is something called as an wound wait scheme. So here, older transaction sort of forcibly rolls back your younger transaction instead of waiting for it, right? And but younger transactions may wait for the older ones, right? So both do they do prevent the deadlocks, and depending on situations, you may pick one over the other, right? So these are just to for your information, and as I said before, these are the same deadlock prevention schemes which you might have already studied in your operating systems course. Okay. Okay, so one thing to note is that both in wait and die and wound and wait schemes, a rolled back transaction is restarted with its original timestamp. Because if this is not happening, then a transaction will just keep on getting killed. There is a chance it may have that, right? So essentially, when we have this and younger transaction, will eventually have the oldest timestamp among the competing transactions. So this way, everybody gets a chance to finish up their process. Right? So this statement you should remember very very carefully. Okay. Okay. And there are some other timeout based schemes also. These are self-explanatory. I don't have to